Assalamu alaikum and a very good day to our lecturer. Today, our group will be presenting our case study on the Tacoma Narrows Bridge for DMID 2853 Mechanics of Materials. Our team consists of four members, myself, Muhammad Amshah, Naufal Hakimi, Lukman and Sharveshan. I will be covering our first section, which includes the introduction, specifications, and the collapse narrative. I will now move into our second slide. The original Tacoma Narrows Bridge opened on July 1st, 1940 as the third longest suspension span in the world. Looking at its key specifications, it had a total length of 5,939 feet, which is around 1,810 meters, and a main span of 2,800 feet. The bridge deck width has 39 feet, giving it a critical and historically narrow slenderness ratio of 1 to 72. This made the deck incredibly flexible under lateral loads. The core structural material used was a carbon steel designed by Leon Moiseev. Now, let's move on to the collapse narrative. The bridge was nicknamed Galloping Gertie because structural issues appeared early on. The bridge exhibited significant vertical waving motions even during construction. The collapse date was November 7th, 1940, meaning it tragically collapsed after 4 months of active operation. The environmental trigger was sustained, high crosswinds hitting 42 miles per hour. At exactly 10 o'clock in the morning, the motion shifted. The bridge suddenly changed from a harmless vertical bounce to a violent two-wave torsional twisting motion. The failure mechanism comes down to its shape. The solid H-shape girders trap the wind, creating alternating low-pressure vortices, a phenomenon known as aeroelastic flutter that forced the deck twist up to a 45-degree angle. Finally, at the ultimate limit around 11 o'clock in the morning, the structural connections and suspender cables reached their breaking point, causing the main span to tear away and collapse completely. This failure structural limit effectively proved that aerodynamics cannot be separated from pure material strength. That wraps up my section, and I will hand it over to Sharveshan. Thank you.
Hi everyone, I'm Sharvishan. In this video, I'll walk you through a practical calculation to show exactly why the Nakamo Narrows bridge twisted and failed. So we are going to model a section of the bridge deck as a simple beam. The two main forces we are concerned with are the load on the bridge and the span length between the towers. As you will see, increasing either of these will dramatically increases the internal force. So we should let's define our variables. We have a bridge section that is 100 meters long, and this is our span length, which is the L. Okay, so the bridge deck and the traffic on it apply a uniformly distributed load of 200 kilonewtons per meter. To find out the bridge is most likely to break, we need to calculate the maximum bending moment, which happens right in the middle of the span. So the formula we use to calculate is M max equals to weight multiplied by length, which is squared by over 8. So we should just plug in our numbers. We have 200 multiplied by 100 squared divided by 8. So that gives us a maximum bending moment of 250 kilonewton meters. Now this is where the danger lies. Notice the length is squared. This is the mathematical reality we discussed earlier. If we increased the span length from 100 meters to just 150 meters, the moment wouldn't just increase by 50%. Because it is squared, the moment would more than the double. This means that on a windy day, the wind loading, which is the weight, pushes down harder, and the long span length, which is our L, magnifies that force drastically. It creates huge internal stresses that the bridge structure has to fight. And once we know the bending moment, we can see the actual stress on the steel using the flexure formula so once we know the bending moment, we can see that the actual stress on the steel using the flexure formula, using stress equals to M times Y over moment of inertia. So M is our bending moment and Y is the neutral axis. Okay, so taking our moment of 250,000 and using standard values for the bridge geometry, we get a stress value of over 333,000 kilonewtons per square meter. That is an enormous amount of stress. It means the top of the steel beam is being crushed by compression and the bottom is being torn apart by tension. So yeah, that's all from me. That's all the explanation. Thank you so much.
My name is Nopal Kimi and I will explain the beam geometry and maximum stress of the Tacoma narrow bridge. First, look at the beam cross section. The Tacoma narrow bridge used solid brake girders with a depth of approximately 2.4 meters instead of open truss brake design. Because the sides were solid, wind could not pass through the bridge. Instead, the bridge deck behaved like an airplane wing, creating aerodynamic lift and torsional oscillation. As the wind speed increased, the twisting motion became larger, eventually caused structural instability. Next is the maximum stress. Maximum stress is the highest internal stress experienced by a structural member when it is subjected to external load. The bending stress is calculated using the formula sigma equal my over I, where sigma represented by bending stress, m is the bending moment, y is the distance from the natural axis, and I is the second moment of area of the beam. From this equation, we can understand that when the bending moment increases, the bending stress also increases. During the strong wind, the Tacoma narrow bridge experienced continuous twisting, which produced higher bending moment and increased internal stress acting on the bridge. Next, I will explain the yield stress and the point of failure. Yield stress is the stress at which steel begins to perform permanently. For the structural steel used in the Tacoma narrow bridge, the yield stress was approximately 250 megapascal. When the internal stress approaches or exceeds the yield stress, the material can no longer return to its original shape. Continuous twisting causes permanent deformation, fatigue, cracking, and weaken the bridge connection. Finally, on 7 November 1940, the wind speed approximately 64 km per hour generated aeroelastic flutter. The oscillation became uncontrollable until the suspender and bridge deck failed, causing a large section of the bridge collapse into perjured sound. So the conclusion is, the collapse of Tacoma narrow bridge demonstrated that bridge safety depends not only on structural strength but also on aerodynamic behavior. The failure highlighted the importance of considering beam geometry, bending stress, yield stress, and wind-induced vibration during bridge design. Today, modern suspension bridges use open truss bridge or streamlined box girders to improve aerodynamic stability and structural safety.